What happens to the structure and composition of the electrode materials during the intercalation/deintercalation process, and how does this affect the longevity and capacity of the battery? How does the reversible intercalation/deintercalation of ions impact the cycle life and capacity retention of sodium-ion batteries? Why is the number of ions that can reversibly intercalate/deintercalate in the electrodes crucial for determining the capacity and cycle life of secondary batteries? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the stability of the active material in the electrode influence the battery's overall performance over multiple charge and discharge cycles? What does the theoretical specific capacity of a material represent, and how can it be calculated using the formula theory equals NF 3.6m1:1? What do the variables in this formula N, F, and M represent, and how do they contribute to the calculation of the theoretical capacity of the battery material? How can understanding the theoretical specific capacity of sodium-ion battery materials guide researchers in selecting the best materials for high-performance batteries? How does the molecular weight of the substance, M, affect the theoretical capacity, and why is it a key factor in determining the performance of sodium-ion batteries? What are the essential characteristics that an ideal cathode material for sodium-ion batteries should possess, and how do these characteristics contribute to the overall performance of the battery? How does the Gibbs free energy of the intercalation reaction affect the potential difference between the cathode and anode, and why is this important for providing a higher battery voltage? What does it mean for the Gibbs free energy variation, delta G, of the sodium-ion intercalation reaction to be smaller, and how does this contribute to a larger amount of sodium-ion intercalation? Why is it important for the electrode potential to be less dependent on the amount of sodium-ion intercalation, and how does this help ensure a higher electrochemical capacity and stable charging/discharging voltage for the battery? How does the crystal structure of the cathode material, specifically layered or large aperture tunnel structures, affect the diffusion and migration coefficients of sodium ions? And why is this important for maintaining a higher diffusion rate and good electronic conductivity? How do these factors contribute to the fast charging and discharging performance of sodium-ion batteries? Why is it essential for the cathode material to experience minimal volume changes during sodium-ion intercalation and deintercalation, and how does this impact the cycle reversibility and long-term cycle performance of the battery?